So we will resume our discussion on Bayesian estimation and Bayesian linear regression, and very briefly we had talked about this map or maximum a posteriori estimation in the last class. What are the different components of map vis-a-vis maximum likelihood estimation? We talked of prior distributions, we hinted towards something called conjugate priors, and all this was we started all this discussion in the coin tossing example just because it is easier to relate, and then we will move on to linear regression. So very briefly, the idea behind coin tossing example, the log likelihood we had derived given the exact outcomes of the n coin tosses. So there are n coin tosses and we assume that we know which of these had heads. Okay, heads. So we assume that we know exactly the outcomes of each of the coin tosses, and they total to k heads, the rest are all tails. So in this was basically our maximum likelihood estimation. We are able to sum up over all the coin tosses because we knew exact outcomes. Okay. Your coin is safely with the TA. But suppose we did not know which k tosses yielded the heads. All I am told you is a sum total. Okay. So there were some k heads that landed. So how would you modify the log likelihood? So can I do a summation over all the coin tosses? A log, basically a summation over the log. Is it possible? If I didn't know which of the n coin tosses yielded heads, how would the log likelihood change? You have heard of the binomial distribution? So what is the distribution about? Yeah, but so there is a set of n from where you choose k, and how many ways can you choose these k? N choose k, nck, right? I won't have this summation anymore because I won't know exactly which of the coin tosses yielded heads, but I know that some k yielded heads. So how would the log likelihood change? I will put a log outside. What will be inside the log? There will be an n choose k into, okay, so theta to the power k 1 minus theta to the power n minus k. Is that clear? That's what we will have if we did not know which tosses yielded the k heads. So this is what I was trying to drive. If we do not know which k tosses yielded heads, we would have this modification. In either case, you can get the maximum likelihood estimate simply by taking setting the derivative to 0 with respect to theta, and you will find that the answer is the same. Why doesn't the answer change? Whether I know basically whether it's a sequence of Bernoulli trials or whether it's a binomial event, the answer maximum likelihood estimate is the same. Okay, so this is core principle is the same, right? This is a sequence of Bernoulli IID trials, whereas the second case is the binomial trial. In either case the core principle is the same, or more specifically when you set the partial derivative of log likelihood with respect to theta to 0, the n choose k term is independent of theta. Is clear? Okay, so these are the Bernoulli trial outcomes. We have some 100 trials, of which 20 were successes, which is heads, 80 were failures, which are tails, right? And in this case it's 20 out of 100. Now there is an underlying theta 0.3 which actually was used to generate the outcomes. Okay, so what is the maximum likelihood estimate here? 0.2. What should it have been? 0.3. There is a slight deviation, right? Okay, this is the Bernoulli outcome and we are not very happy. So then we move on to the map estimation, where we say that we have a prior idea. So in the simulation I had, theta was 0.3 whereas theta MLE was 0.2, right? And I say, well, let me model a prior belief about the theta. So can we get theta map closer to theta through a prior belief? So my prior belief could be, for example, that it's a fair coin, it's not as bad as it appears, 20 out of 100 heads, right? And that's where we were in the last class. Can we factor in a more fair coin prior? So what theta map does is it says, well, there is a posterior distribution on the theta after you have observed the data. Okay, so likelihood recall was all about modeling your observation. So we also call this the probability of data given theta. Now we are saying, well, let us try and model a p of theta, and when you combine the two, you can get probability of theta given the data, the posterior, which we know is proportional to p of theta and p of data given the theta. This is where we concluded in the last class. Okay, so this is the Bayesian way. The maximum a posteriori estimate says, well, first of all I will have a posterior distribution on theta based on some prior on theta. This is my prior, p of theta given data is my posterior, and my map estimate is that value of theta which maximizes where the posterior peaks. This is where the posterior peaks. Okay, so this has two components. The theta map is an argmax over theta of p of d given theta and p of theta, and by now you should be very familiar that the moment I say p of theta given d but view it as a function of theta, is nothing but the likelihood function. This is the likelihood function, and if I take the log of that, I get the log likelihood. So since theta map is argmax either in the original space or in the log space, we have seen the equivalence of these two in tutorial 1. Okay. So in the posterior, you still have a role for the prior or the log prior. So it's, as you see, it's very similar to MLE. It's very similar to MLE except for this term, the second term, log prior term. Okay, and let's now see the effect graphically before we move on to mathematical derivation. So I'll go back to the same example, and as I said, for us the motivation is that theta originally was 0.3, I'm able to get to only 0.2. So now I'm going to model some prior. Now prior says, well, I have so what this prior means we had seen in the end of last class and we'll continue that today. But effectively what we are saying is, well, I very firmly believe that this was a fair coin, okay. And then what is the effect on the posterior? Is this visible from behind? So you see the green is a prior, it's a distribution, we are dealing with distributions. And now the originally what was the MLE? 0.2. But some prior like this, it's pulling the distribution over the theta more towards the prior. So this posterior is somewhat pulled towards the prior, and it's peaking away from 0.2. It's peaking more towards 0.3. Do you see this? This is the effect we want. The form of the prior is what we saw in the end of last class, but we'll get to it again. But this is the effect we want. This is a desired effect. We want to pull the posterior towards a fairer coin, and in some sense, in this case, we are also pulling the posterior towards to peak to closer to 0.3. Okay, so I'll just paste this. Okay, so this is exactly the picture we want. So theta map which is greater than 0.2 is closer to 0.3, may not have yet coincided with 0.3, and this effect is because of the prior. In fact, it's due to the prior and also because of this Bayesian framework, where everything is now, everything we talk about the parameters is through a distribution. Is this clear? And we are a theta map is only one point here. We are not talking about the entire distribution when we talk of theta map, but theta map is because of a distribution, is where the posterior distribution peaks. Is that clear? I mean, I would like that the intuitive picture is clear to everyone before we get lost into any mathematical details. Why the green is what it is, we will see. Okay. Okay, so now in the last class we said that somehow if we can model our prior in terms of some hypothetical number of heads and hypothetical number of tails, then we get something called beta distribution. So here the prior p theta is modulo some multiplicative normalizing factor theta raised to alpha minus 1 and 1 minus theta raised to beta minus 1. So think of this alpha minus 1 as some kind of prior number of heads very loosely and number of tails, right, or rather beta. As I said, this is very loosely speaking. So your prior, does it look like your Bernoulli or sequence of Bernoulli? The prior has a feel of the sequence of Bernoulli, right? You could also give, I mean, in fact, very soon you will see that it is basically the sequence of Bernoulli or binomial. Effectively, we are talking about the same thing. We are talking about alpha minus 1 heads out of alpha plus beta minus 2 coin tosses, right. So P theta looks similar to the binomial or sequence of Bernoulli trials. A similar form. Okay, the 1 upon C turns out will be an equivalent to n choose k. N choose k also is a normalizer, by the way. I mean, from the point of view of binomial, it's a normalizer. It basically ensures that sum across different. Also, sorry, this is yeah. If you kind of count it across all possible values of k, the sum should be 1. So the C will be like 1 upon C, will act like this normalizer. Okay, so just to kind of compare this form, the main form, and then there is this compensation in the form of the normalizer. Okay, so when you have this form, what do you expect the probability of theta given d to look like? What will it look like? So you would expect the exponents to add up, right? Of course, you will have some other new normalizer, 1 upon C prime theta raised to alpha plus k minus 1 minus theta raised to n minus k plus beta minus 1. So this is hinting towards conjugacy. So if d given theta follows a distribution d1 and theta follows a distribution d2, then p theta is a conjugate prior of d1 if the distribution of p theta given d follows a distribution d2. Okay, so again let me map all this discussion to what we have here. So this distribution is what we are referring to as d2. This distribution is d1. Right, and the prior is also the d2. So prior and posterior we would like to have d2, form d2, and the likelihood to have the form d1. So when given a form d2 for the prior, when given a form d1 for the likelihood, if you adapt the form d2 for the prior, the posterior has the same form d2, then you call the p theta to be a conjugate prior or d2 to be a conjugate prior for d1, the form d2 for d1. Okay. So summarily what we are saying is, this had a form D1, I pick a form D2 for P theta, and this results in a form D2 for P theta given D. Then in that case D2 and D1 exhibit conjugacy. Okay, so we have seen one, we will see examples. Use that side of the board. Okay. Now what exactly is this C? Okay, so for those interested, the C is referred to as the beta function. You have 1 upon C here, this C is referred to as the beta function, and this beta is again expressed in terms of another function called gamma, which is directly related to the factorial function. How many of you have come across the gamma form? It's a gamma function. So gamma function coincides, gamma n coincides with n minus 1 factorial for integral values of n, positive integral values of n. Okay. Now what does this beta look like for different values of alpha and beta? So beta 1 1 is a uniform distribution. Okay, so this this uniform distribution it's not been shown in this figure, I have just added it. That's a uniform distribution. So basically it's as almost like I don't have very strong prior or bias about what the coin should behave like. Let's look at some other configurations. Moment you have alpha equal to beta, what do you expect? So do you see this curve? Okay, this is alpha equals beta equals 2, and as you can see this peaks at 0.5. So in general for alpha equals beta, okay, but alpha equals beta greater than 1, the peak is at 0.5, which means that the prior is modeling a fair coin, right? But the larger the value of alpha and beta, what did you expect? The sharper the peak. So peak sharpens. So for very large value of alpha and beta, it will almost become like a Dirac delta distribution at 0.5. At 0.5 you get a Dirac delta distribution. Okay. So alpha and beta, the magnitude of alpha and beta, they talk about what do they symbolize? The prior, belief, count, they are like the count, the strength of the prior belief. So alpha equals beta, the magnitude is the strength, you can say the count of prior belief. and in general you can show that alpha divided by alpha plus beta is the peak of the prior. Well, there are actually two different things. There is alpha, there is a peak, and there is also the average value. Okay, so I will leave you to figure out, but the two numbers we deal with, one is alpha divided by alpha plus beta, the other is alpha minus 1 divided by alpha plus beta minus 2. So one is the peak, the other is the average value, the expected value, but both behave similarly at 0.5. Theta map would be what, greater than, yes, theta MLE? Would it be always greater than theta MLE? So if, for example, if we find that the map, the peak of the prior is greater than the peak of the likelihood, which is the MLE estimate, then the map will be pushed towards the peak of the prior. Okay, so this explains why theta map is greater than theta MLE when theta MLE is less than peak of prior. Okay, and that's exactly what we observed here, this figure. Okay, I mean this form of prior was a really strong prior, where I said it has to be, it's not even a fair coin assumption. It's basically saying that the, it's just heads. I just believe it has to be only heads. That's what it symbolizes, or nearly only heads. That's a green curve here. So green curve here. So can you guess what this green curve, what alpha beta it should have? Beta tending to 0 and alpha very large, right? Okay, so this is certainly not a fair coin assumption that we made here in our simulation. Now there are also other estimators. As I said, there is this map estimator which is about the peak. We have kind of covered this. We have covered MLE. What we won't cover is, we have covered Bayes estimator to some extent, it is the expected value or also the mean of the posterior. So we won't delve into it in details, but the pure Bayesian estimator we won't talk about. I am just going to give you a hint what it is. See what MAP and MLE did was it said I will find a point estimate. MAP and Bayes in particular said I have a posterior distribution, but I will only pick one point from that posterior, right. Here is a posterior, I mean I could have used the entire distribution, but I said no, I am going to pick one point from here. Pure Bayesian says no, I will be Bayesian all through. I will use this entire red distribution, and how will I use it? I will use it for a new query point. So let us say I have a new query point and I want to find, I want to regress on it. So P of x given d is going to be integral over all the values of theta of the posterior. Okay. So think of this as expectation with respect to posterior. That is what we are doing here. Okay, so this is being pure Bayesian. In the previous two cases, I said I had a posterior and I pick a point. They just pick points, whereas this one says I am going to use the distribution as it is. Is that clear? That is it. We will not delve into it further. So let us now complete our table of conjugate priors. As I said, binomial or sequence of Bernoulli, we have beta. Now if imagine I toss the dice instead of a coin. Okay. So this would correspond and you could also count the number of ones, count the number of threes, right. So you could have multivariate Bernoulli or multinomial, depends, if you count it you get multinomial. Multinomial is extension of binomial, multivariate Bernoulli is extension of Bernoulli, right. Now for this there is an extension of beta called the Dirichlet. This is a Dirichlet prior. It is a Dirichlet distribution which forms a conjugate prior for these cases, multinomial, also categorical, that is also in the same family. For these you can get Dirichlet prior. Now beta, our favorite beta, is also conjugate for some other distribution called the geometric distribution. We will see if there is a need. Now let us focus our attention on what we really need for regression. Which of these distributions did we invoke for a probabilistic interpretation of linear regression? The normal. And there we had a normal distribution on the error, right. This is what we had, and this led to a normal distribution on the probability of y given x. Remember, this is what we had. Now we will talk about a prior on W. So again recall, what did we believe the W should behave like? A prior belief on W's was that their magnitude should be small. There is no need to artificially bloat up a W just for the sake of fitting, right. Let me show that once again to you. You might recall these plots, right, and we found that W's tend to be very large, unnecessarily large, even when there is no need. Okay, so let me copy this image. Okay, in fact I will also show you what the W's turned out to be here. So your W's, here, the W's were very large, W1, W2, needlessly large, as you say, minus 7.5 raised to 10 raised to 5 and so on, right. Both magnitudes kept increasing with higher order, higher degree polynomials. So our prior here what was our prior? Let us speak in plain English. In plain English, our prior is that Wi should tend to 0 unless there is a need from the data set, unless the data set says that I need very complex fits. Okay, so I want to model this prior on Wi. Is this clear? So this is exactly where my question is. Okay, what will be a conjugate prior for epsilon? So let us say epsilon is normal. I will look at the likelihood which will have a particular form, the exponentiated form with the normal normal components or Gaussian components, what would be you think the conjugate prior, and write conjugate prior for W, and we are talking about W here. So W is basically sitting in the mean, right? So what we are looking for is variance fixed, conjugate prior for mean of a Gaussian. I hope by now you are fairly comfortable with using Gaussian and normal interchangeably. What do you think will be this? Huh? Okay, Gaussian. How many of you think this will be a Gaussian? Okay, fairly large number. And indeed it is Gaussian. And there are multiple reasons why this is so, but very much like what we had, this multiplicative form, in the case of Gaussian, the log likelihood, okay. So let us say variance is fixed. What does this look like? This is a form, okay, you can also have a product here, product over i's. Now if for the mu also had a Gaussian, I do something like this, right? I do probability of mu given data, where by mu I mean W, so the W transpose phi x is sitting in the mu part, that is why I am talking about mu here. So this will be proportional to probability of the prior distribution on mu, which is what I am seeking. Right, this entire thing is the probability of data given the mu. So you can show that because you are dealing with a product of exponentiated forms, if you add one more exponentiated form, you will be able to absorb the new exponentiated form here, do some quadratic, basically complete squares. The process of completing squares, how many of you have come across completing squares? I give you one component, another component, both are squared form, I sum them up and show a new squared form. You have done this manipulation before, right? So this is the trick is completion of squares. That is the trick. Okay, so the answer indeed is normal, and I'm going to quickly illustrate this. Okay, so the answer, as I said, is normal. So there is a summary of what we are trying to say. Before computing the map estimate for linear regression, let us find the conjugate prior for Gaussian likelihood. Let probability of x be normal. So I'm before jumping to linear regression, I am taking a simple Gaussian case. Okay. So I know that the maximum likelihood estimate is simply the average of the measurements, the observations, and sigma square MLE, maximum likelihood estimate, is just the again the intuitive empirical variance. Okay, so suppose you are told that the conjugate prior for a fixed value of variance is normal. I also refer this variance is sometimes we are going to refer to sigma square as inverse of the precision. Okay, so sigma square is variance, and if you look at the normal distribution, we know that most 99.9% points are within 3 sigma square, right? So 1 upon sigma square is the precision. So higher the value of sigma square, lower the value of precision. The more you are spread out, the less precise you are. The smaller the value of sigma square, the more precise you are. So therefore 1 upon sigma square is also modeling precision. This is important because you will see that in our completion of squares, 1 upon sigma square will play a more important role than sigma square. I mean it's obvious here, it's 1 upon sigma square t sitting here. So let's try and now everyone has to work this out by hand, okay. So here is the what we have written on the board. We have the prior probability of mu, this is what we have been referring to as D2, the D1 corresponds to the probability of data given mu comma sigma square, and we believe that since normal is its own conjugate, the posterior distribution probability of mu given data D2, what is the form of that? What is it proportional to? Probability of data given mu into probability of mu. Okay, so now we are going to write this down. This is multiplication. So just note that we have a prior distribution for mu in terms of some mu naught and sigma naught square. And all you will have is those corresponding components sticking in here. That is it, the product of the two. Okay, so now I want you to tell me what the form of the posterior, okay, so we already claimed here normal for fixed sigma square will give you normal, right. Now you have to prove, we have to give some expression for the posterior. So what will be the map estimate, or let us call just posterior? What will be mu posterior looking like? What will sigma square posterior look like when let us say xi is distributed as mu sigma square for fixed sigma square and p theta, which is mu, is distributed as mu naught sigma naught square. This is a story we want to complete. We want to be able to find these forms. Okay. So in other words, what we are trying to say is this, all this put together should look like very nice form 1 upon 2 pi sigma, now we will call it posterior, sigma posterior square exp of minus mu posterior of 2 sigma posterior square. Okay, so what we want is this transformation from yellow to green, and the transformation is through the data. This P of D given mu is what led to this transformation. I saw the data and I had a posterior. Otherwise the forms look both normal. My sigma mu naught has become mu post, sigma naught square has become sigma square post. So how do I find that? Completion of squares. I'm going to basically we'll do something simpler. We'll only match coefficients of the squares. That's it. So okay, this is what we want. Yeah, this is what we have, and this is where we'll try and match the coefficients. So let's do this. Okay, so this is the form, our reference equality, and we're going to match coefficients of sigma square. Please help me. Let's do this quickly. So we just want to match coefficients of mu square. Anything that involves mu and square. It's square. It's proportional to. There's some proportionality. Good point. It's proportional to. Please feel free to ask the TAs or me if you have any doubts at this point. Everything that you require is on the board. Sorry, on the slide. You don't need anything beyond the slide to be able to answer this question and answer a series of questions. So from this first summation, how many sigma squares will I get? M sigma squares? So m mu squares, that's what I meant. M. So I'll get m by 2 sigma square mu square minus on the right hand side. Okay. So since we are anyways matching only coefficients, I'll remove this mu square here. This is what we have. I'll just writing it more neatly. You can get rid of the 2's, the negatives and all that. M upon sigma square plus 1 upon sigma naught square is 1 upon sigma posterior square. So the posterior precision is m times the original precision, the fixed precision, m times the fixed precision. This posterior precision is m times the fixed precision plus the prior precision. In plain English, right? That's what we are saying. No, we can equate it for the coefficients, for sigma square and sigma. Oh, sorry, mu square and mu. Because we want the form to be. I mean, if at all the posterior is a normal, we'll need that. We'll need exact equality. Okay. So again. M times fixed variance plus sorry, not variance, fixed precision we are talking about equating the exponential form, right? And we want the mu posterior to have exactly, I mean, if we believe, so we have not proved that the posterior will have a normal distribution, that's just intuition. I just give the intuition, I am not proving that here. But if it has a Gaussian form, then you would like equality. That's it, that's all we are saying. So this is the prior precision. And you will see in many cases it's just easier to talk in terms of precision. And this is the posterior precision. So it's interesting. If you make m observations, your precision of the posterior increases, right? You get more precision after making more observations relative to the prior, which makes sense. Again I go back to what we are trying to show here. I mean, we showed this for the Bernoulli. Let's just quickly show this for Gaussian. So this is Gaussian, this is Gaussian data. This is the prior distribution. This is some prior distribution. This is on the mean for a fixed variance. Okay, and you can see it spread out a bit. I am not too sure. Now this is the posterior, the analytic posterior distribution. You can see that it's more focused. It has higher precision. And the exact values are here. I can make the notebook available to you. This is what we mean. It's more focused. It's higher precision. So this is what we get. Precision as weighted linear combination. I hope this is clear. What about coefficients of mu? What happens if you match them? So what is the coefficient from here? From the first component for the mu, not mu square, only mu. I think it will be 2 by 2 sigma square summation I equals 1 to m of xi. Is that correct? For the second one, plus 2 by 2 mu naught square, that's mu naught, right? What will be on the right hand side? So forget the okay, I mean we are just talking about the exponent. And here summation xi upon, there is no summation here. It's just 2 mu posterior. There is no m here even. Upon 2 sigma square posterior. This is from the right hand side. What do you get? So what is this basically? Xi, summation xi, let us say you divide by m. I can do the following. I can multiply by m and then divide the whole thing by m also. What is summation xi divided by m? The mean. But don't go, no longer mean, it's a maximum likelihood estimate of the mean, right? Mu MLE. This is the prior mean. So my posterior is a weighted, is it a weighted average? Not exactly, but it's a weighted linear combination. Okay, let's write this a bit more neatly. Okay, so this is a weighted linear combination. And again go back to the, that is what is happening, the mu MLE, sorry, mu posterior is a combination of what you observed, mu naught, and some observations in the data which is probably tending to the other side. We saw that for coin tossing and all, so here you are kind of getting somewhere in between. Okay, so this is what you get. Mu MLE divided into m divided by sigma square. that is the first component, mu naught by sigma naught square. Now I think it turned out to be actually a weighted average if you also substitute for sigma posterior square, verify that. Okay, so coming back, why did we get into map estimation? We want to do something for regression. So recall that for linear regression, if epsilon j was normally distributed, each way yj is drawn from the tends to be drawn from this Gaussian prior, and we had the MLE estimation, which is the least square estimation. Now what is our belief about W? We believe Wj should tend to 0 unless necessary, right? But let us try and write this in a Bayesian sense, which means write a prior on Wj. What will be a natural prior on Wj? We have already seen that for normal the conjugate prior is normal. We know how to find the posterior parameters. Okay. So we can model Wj as normal with 0 mean. Okay, and what I will do is I will say 1 upon lambda will be the variance. So lambda is the precision. I will use lambda as a precision, as the sigma square is floating everywhere, we need variety, so I will put lambda there. So lambda is the precision of Wj. It is normally distributed around 0. We are saying this is basically it is saying that 1 upon lambda is a spread variance, lambda is a precision. Okay, and now you believe that there should be some more legwork which I have to do to get to a posterior. So I am going to skip some steps, and you have to believe me that if I do the following, so let us say probability of W, now I am going to model all the W's together, it is not just one W, a vector of W's, right. So probability of W, when you stack them on top of each other, is basically probability of W1, W2, Wp all put together, and I will assume that each of these is independent and identically distributed. Each Wj is independent of the other Wj. So this will give me a product over I equals 1 to p of some normal distribution around mean and variance lambda. So this is we should write this Wi given 0 lambda. Okay, and now if I just extrapolate this product, I could more compactly write this way. Extrapolate this into a multivariate Gaussian, this is called a multivariate Gaussian, but it is nothing but a product of independent Gaussians because it has a covariance matrix which is 1 upon lambda I is the identity matrix. Okay, so I mean just trust that these are the same. If you do not understand this form, this form is easy to understand because it is a product of P independent Gaussians. Okay, and thereafter I can actually write down what that means, right. Rest is nothing to do with vector notation, multivariate distribution as such, just writing this down, the same form. So what you observe is finally this form is the most important for us. What do you observe here? You observe a form exp of minus lambda by 2 norm W square. This is the form you observe. Okay. So all we are saying is this form, if you plug it in here, log of P of W, what do you expect? If I take log of x of this, what do you get? Just minus lambda by 2 norm square. That is the key. The key is that form. Okay, so we just quickly substitute. So I am looking at W map, which is argmax over W of probability of data given a distribution on given W into probability of W, which is the same as argmax over W. Let me take this first, of log of probability of W, and now I am going to the log space, plus log of probability of data given W what is log of probability of W? It's proportional to, I mean, so it looks something like minus lambda by 2 norm W square, and what do I know about the form of log of probability of W? It's like least square, right, plus phi W minus. So this is the form we get as a result of map estimation. Okay, a small one more point actually, there's a small factor you need to consider. You need to consider the fact that epsilon given, so the distribution for epsilon, distribution for y is basically centered around W transpose phi x and a sigma square. There is a sigma square component. So it just turns out that if you work things out carefully, you will have a sigma square as well. So it is not just minus lambda minus sigma square lambda. The sigma square which was associated with the epsilon will also come here. Okay, because after all this y, this component, there is a sigma square that comes here. That sigma square with some kind of multiplying it throughout, you will get sigma square in the numerator along with lambda. So this is what I wanted to show, that W map is basically this form, is the original sum of square error, this entire component, which we are all familiar with right now, plus a new component where you have lambda sigma square so this lambda 1 by 2, lambda sigma square by 2 into norm W square. What we will do is just replace lambda sigma square with a simpler lambda. We will combine the lambda and sigma square. But this is ridge regression. So this is ridge regression. Is this clear? So you have seen the mathematical equivalence. Now we will not keep doing this exercise as a long exercise, but we have shown how a simple hack like adding this penalty is amounting to posterior estimation through a Bayesian framework, and this is not something we will keep doing for every, so you can assume hereafter that this regularization that we talked about is a way that you avoid, that you use to avoid complex models. Complex models could lead to overfitting, how to counter, and that is what we had shown here, is through regularization. So here is the complex model, the very complex models is what we call overfitting. and how to counter. And let us now just add this form this form W map that we just added, where we had sigma square norm W square, and now let us look at the form, what we get. Okay, so this entire transformation has been obtained simply by adding a penalty term. Actually, this negative won't be there. You won't have a negative here because you are maximizing. You will have this 1/2 lambda W square. And what do you observe on the right hand side? I will show the bigger figure. Now, what do you observe when you add this for some value of lambda? So, let us say small value, when I have small value of lambda, the effect is small, but as I add larger values of lambda, you almost get a straight line. You are not dancing to the tune of the data set, which means you are more robust. Okay, so this is degree, I think degree 5 or something polynomial. This is a degree 5 polynomial. Oh, so it's 20, 18 of them. Okay, and as you increase, you can see that the lambda is increasing here. As you increase the value of the lambda, your variation with respect to data is decreasing. That is the key. In general, you can have this. You could have any loss, and we looked at squared loss, and you could have any regularization. We looked at this Euclidean norm square of W as a regularization. So this is a popular penalty term, Euclidean square, norm square, Euclidean norm square. But there is also another form which you have in your assignment, which is the 1 norm square. Okay, so lambda, not 1 norm square, just the 1 norm, lambda 1 norm. So it's the lasso, it's called the lasso, and it also corresponds to map estimate under some other prior called the Laplace prior, which again we will not get into, but Laplace has some other distribution. So Laplace, instead of Gaussian, it has this absolute value, mu I minus sigma absolute value. In fact, there is a very famous, this is a cartoon, Gaussian estimation. Gaussian model is considered like a hare. All of you know the story of hare and the tortoise, right? So Laplace is considered the tortoise, slow but steady, whereas hare is very fast, very quick to estimate. You just put this norm lambda by 2 sigma norms W square, you get the estimate. You get closed form as well, but you do not get closed form with the Laplace. So Laplace yields more sparsity. Okay, and I'll discuss a little bit, I'll discuss about that more in the next class, but you may have to use this in the assignment today, which is not necessarily due today, but the Laplace basically has these corners. It has this is how the level curves of Laplace look like, and I'll explain more of that in the next class. But the way to optimize for lasso is very simple. I mean, it is iterative. There's no closed form solution. I think the algorithm is put out, right, the iterative scaling, but the idea is you do thresholding. At every iteration you do a thresholding using the lambdas. It's something we can, I'll continue into the lab today, how exactly you have to implement lasso, the optimizer for lasso. We'll just take a quiz now.